For 2 solid centuries, some of the absolute giants of science were locked in this epic debate over a question that honestly seems pretty basic today. It was like a massive scientific cold case that defined an entire era. And the question at the heart of it all was, what is light, really? And that's what it all boiled down to. Is light a particle, or is it a wave? It seems like a simple choice, but the answer was going to completely change how we see the universe. So, which one is it? Let's dive into the evidence and see for ourselves. All right, so for a very, very long time, there was a clear favorite in this fight. This was the theory pushed by the legend himself, Isaac Newton. And his idea was so powerful, so intuitive, that it just completely dominated the world of science for over 100 years. Newton's idea was just elegant. He thought light was made of a stream of tiny little hard particles that he called corpuscles. And this theory was brilliant because it explained all the stuff we see every day. Light travels in a straight line, right? Just like a ball you throw. And when light hits a mirror, it bounces off at the exact same angle it hit. Again, just like a ball bouncing off a wall. It just felt right. It made perfect sense. So that's the key word here, corpuscles. It's a great name, isn't it? Just think of light as a stream of microscopic bullets, all flying in a perfectly straight line from, say, a candle or the sun. This super simple, powerful idea was the heart of Newton's whole theory. And the best evidence for the particle theory was something anybody could see for themselves. Seriously, just look at the world on a sunny day. Objects cast these really sharp, clean shadows. And if light is just a stream of tiny particles, well, that's exactly what you'd expect to see. The object just blocks the particles, leaving a perfectly clean edge. Back then, it seemed like there was no other way to explain it. But here's the thing. Even back in Newton's day, there was this other kind of radical idea floating around. A Dutch scientist named Christiaan Huygens came up with a totally different theory. But, going up against Isaac Newton, his idea was pretty much ignored.
Huygens was convinced that light wasn't a particle at all. Nope, he thought it was a wave, spreading out from its source just like ripples in a pond when you toss a stone in. He even imagined these waves traveling through some kind of mysterious, invisible stuff he called the luminiferous ether.
But Huygens' wave theory had one huge, fatal flaw. Think about those pond ripples again. If they hit a big rock, they don't just stop dead, right? They curve and bend around it, filling in the space behind. All waves bend around things. So, if light was a wave, why on earth did it cast such sharp shadows? It just didn't add up, so the whole theory was basically tossed aside. And that bending thing that waves do, it has a name. It's called diffraction. And it's a fundamental property of all waves. The problem was, everyday light didn't seem to diffract. It made sharp shadows, not blurry ones. And because of that, the wave theory just couldn't hold a candle to Newton's particle idea. So for a whole century, the case was pretty much closed. Light is a particle. Done deal. But then, right at the beginning of the 1800s, this English physicist named Thomas Young comes along and designs an experiment so simple, yet so incredibly brilliant, that it was about to blow this whole case wide open again. Young's whole setup was just genius. He took a light source and shined it through a screen with one tiny little slit in it. Then, he took that beam of light and shined it through another screen, but this one had 2 slits right next to each other. So the big question was, what kind of pattern are we going to see on the wall behind it all? Okay, so let's put on our 19th century physicist hats for a second. If light is made of Newton's tiny corpuscles, like microscopic paintballs, what should we see on that final screen? The answer seems totally obvious, right? The little particles would just fly straight through either the left slit or the right slit and hit the screen behind them. You'd just expect to see 2 bright lines, one behind each slit, a perfect copy of the openings. This was it. The moment of truth. The prediction from the particle theory was crystal clear. But when Young actually did the experiment, what he saw was not what anyone expected. Not at all. Instead of 2 simple bright lines, he saw this. A whole series of bright and dark bands spread out across the screen. This stunning pattern was absolute, undeniable proof that something completely different was going on. This was not how particles behave. This was the unmistakable signature of weight. This is a phenomenon called interference. Just picture those 2 sets of pond ripples again. When they meet, sometimes the tops of the waves add up and make a bigger wave. That's what a bright band is.
But other times, the top of one wave means the bottom of another, and they completely cancel each other out, leaving flat water. That's a dark band. Young's experiment proved that light had to be waves, coming from each slit and interfering with each other on the way to the screen. Young's experiment totally changed the game. It was the smoking gun that the wave theory had been missing all along. And over the next few decades, the evidence just kept piling up, putting the final nails in the coffin of Newton's simple particle theory. A really decisive blow came from measuring the speed of light. See, Newton's particle theory predicted that light should actually travel faster in water than in air. But the wave theory predicted the exact opposite, that it would slow down. Well, in the 1850s, Leon Foucault finally did the experiment, and the result was clear as day. Light slows down in water. The wave theory was right again. And then came the grand finale. In the 1860s, the physicist James Clerk Maxwell came up with this incredible theory that unified electricity and magnetism, and his math predicted that there should be these waves of energy that traveled at the exact known speed of light. The conclusion was just inescapable. Light is an electromagnetic wave. So by the end of the 19th century, this 200-year-old mystery was finally put to rest. You had Young's interference pattern, you had Foucault's speed measurements, you had Maxwell's incredible equations. All the evidence pointed in one direction. Case closed. Light is a wave. The consensus was so total, so absolute, that it was summed up with this great quote. To even bring up the idea that light might be a particle was to basically call yourself either a fool who didn't get the science or some kind of super genius who saw something nobody else did. The scientific community was sure. They had their answer. The case was closed for good. But physics was about to be turned completely upside down, and a certain young genius was about to reopen this very case in the most shocking way imaginable. But that's a story for another time.